Anyways, let us. So again, three questions are there. Navkirti, I gave an assignment. Did you do the assignment?
Yes, sir.
Can you share your screen and show the flux lines that you have drawn?
Uh, Sir, I need to join through my mobile. Wait for a minute, sir.
Okay.
Sir, can you please remove me for a minute? The mobile.
Okay. No, Navkirti, this is not what I asked for. I just wanted to draw one. I just wanted you to draw just a pole and the slots of the teeth. That is all. I didn't want you to draw the entire machine. Just a small section of the pole and the slots underneath. So actually, I was planning to show all these things, but I couldn't prepare because I need to make these drawings because I didn't know that today we people have class. I thought of sharing this. Okay, let me. Okay, let us first discuss the questions that I already have, and then we will move over to that. Can you see the question?
Not yet, sir.
Okay. Okay. Now you can see the question.
Yes, sir.
Yeah. So a part of the route array has been given to you, and you are asked to find the range of k for which the system would be stable. So I'm giving you 3 minutes time to solve it. Just solve it and tell me what you are getting. By the time, let me see whether I can make the drawing and show it to you. So have you already done the sum? It is already 3 minutes. 3 minutes is over.
So option B.
Option B. Let's see. So it's very simple. So let us construct the route array first. So I've done this millions of times almost in the previous classes. So what we found that these are the two elements that we have where k is involved. So for the system to be stable, all the poles should lie on the left hand side of the S plane. For that to happen, all the elements in first column of the route array should be positive. So 2k and this element has to be positive. So 2k has to be greater than 0 and this element also has to be greater than 0. So we can find that k is for this factor to be greater than 0, you see k has to be greater than half. If k is greater than half, then this becomes uh, positive, and this will be positive if k is positive. So if k is greater than half, this factor will be greater than 0, So the correct option is D. It is not B, it is D. Navkirti, why are you committing mistakes in these sums? You shouldn't do that. You should practice more, I think. You shouldn't commit mistakes in this sum. These are very scoring things.
Yes, sir.
Okay. So let us move on to the next sum. This is the second order LTI system whose state space equations has been given to us. So, and this x1 and x2 are the state variables, u is the input variable. Okay. So, and the output is given to you as c equal to x1 of t. And you have to find out whether it is controllable or observable, observable or controllable, both controllable and observable, neither controllable or observable. So, which would be the correct option? Try to do it. I am again giving you 3 minutes. That is, uh, so I will be asking you after 7:31. I will be asking you. It is already 7:32. What is your answer, Navkirti?
So 1 minute, I'm solving. Sir, it's controllable.
Yes. What are the observability?
Sir, for a system to be controllable, the
Yes.
C matrix order and the determinant must be equal. Determinant must not be zero, and the order should be equal to the number of terms
Correct. Correct.
order.
What about the observability? Whether can you tell whether the system is observable or not? Controllability. Okay, you have told that it is controllable. What can you tell about its observability? Is it observable or is it not observable?
About C matrix, some can say.
So let us see. Okay, so these are the state space equation that I have written in matrix form. From here we find that A matrix is this minus 2 0 0 minus 1, a 2 cross 2 matrix, and the B matrix is a column matrix having two rows and one column. So it has the elements 3 and 1. C is a row matrix having two columns, that is and the elements are 1 and 0. So let us find the controllability matrix now. So that is the first column of the matrix would be the B matrix, and the second column would be A into B. So if you perform this operation A into B, you get minus 6 and minus 1, and B matrix you already have 3 and 1. So you see that system is controllable. If you look at the observability matrix, the observability matrix is a so you have the element C on the first row, and the elements of the operation C into A, that is multiplication of the matrix C and A, would be the second row. So if you do that, you see that this would be the observability matrix. So you find that the rank of the observability matrix is not equal to the order of the system, so it is not observable. So the correct option is A. Okay, let us move on to the next question. Okay, so this is the next question. You need to find out the location of the breakaway point. The open loop transfer function has been given to you, and HS is set to 1. That is a unity feedback system. So you need to find out the position of the breakaway point in the root locus diagram. I'm giving you 3 minutes again. So at 7:38, I will be asking you. So it is 7:39. Have you done this sum?
No, sir.
So have you approached it? How are you approaching it?
So making factors in the denominator and then pole minus zeros and then finding the centroid. After that,
Why do you need to find centroids and all? Why do you need that? You do not need all those things, right? You just need to find the location of breakaway points. So can you, whenever this kind of question, whenever a question of root locus is being asked, try to draw a rough sketch of the root locus. It will give you the picture how this the root locus would look like. Okay.
yes, sir, I just
Yeah.
needed to 1 over 1 plus g of s, h of s, and then calculating k from that by differentiating it.
Okay. Okay. So let us look at the solution. So you see there is 1 0 at s equal to -2, and there are two complex conjugate poles, -1 plus minus j, right? So there are two poles lying over here, and there's 1 0 lying at s equal to -2. This is the s plane. The real part, this is the real, this axis is the real of s, and this is the imaginary of s. That is j omega axis. So you see there are two poles over here, two complex conjugate poles, and there is 1 0 over here. So how would the root locus look like? Navkirti, any idea? Can you just give a guess how it should look like?
It will start from -2 and then go towards j1 and minus j1.
Where from does a root locus start? Does it start from open loop 0 or open loop pole?
So it starts from open loop poles and then travel towards open loop, sorry, zeros towards infinity.
No, no. I'm asking that where from the root locus will start. You just said that it will start from -2 and it will go towards this. So is it the case or is it the reverse thing that would happen?
So it will start from k is equal to 0, that will open loop poles, and then will go towards
Towards.
open loop zeros.
Right, right. So the root locus should start from here and also from here. The other branch would be the image of this branch, which I'm showing through cursor. It will start from here. It will just wait a minute. It will start from this point. It will meet the real axis somewhere over here, and then one branch would move towards this open loop 0. Another branch will go towards infinity. Right?
Okay, sir.
Is it so? What do you think? No, I do not know. I'm just asking you. Do you agree with my argument or you don't?
Sir, I couldn't get it.
Okay, I'm saying that you see the open loop pole over here, right? This blue blocks that I've marked with my cursor.
Yes, sir.
So the root locus would start from this point. There is one branch of the root locus. One branch of the root locus should start from this point. It would move along the cursor that I am showing. It will move along this portion. It will meet the real axis somewhere over here. There will be another branch moving from -1 minus j, and then it will meet somewhere over here. And then one branch would, because this would be the breaking point, then one branch would move towards the 0, the other branch would move towards infinity. Do you understand now or don't understand?
Yes, sir. Now, sir, but root locus will exist from the odds one, like poles and zero. The sum of them must be odd. In
Right.
that axis, it will exist.
Yes, so over here, you see, in this region, so if I consider this region, there cannot be any root locus in this region, right?
Yes, sir.
Why? Because there are two poles over here, and to the right of these two poles there is no pole. There is zero number of poles or zero, so that is even. So if I am considering this region, so to the right of this region there are two poles. So root locus cannot exist over there. So root locus can only exist in this region,
Yes, sir.
right? So I mean on the real axis, exist means I'm talking about the existence of the root locus on the real axis. Okay, so the root locus would somewhat look like this. It will start from this point. It will meet the real axis somewhere over here. There is another branch will start from this pole. It will meet somewhere at this point, and then it will break away. One branch would move towards -2, other branch would go towards infinity. Is the root locus picture clear now?
Yes, sir.
So do you agree to this? Am I correct in drawing the root locus?
Yes, sir. I'll draw again.
So what point is this? What is
The
what is it?
breakaway point.
No, no. What is the significance? What is the significance of this point? What is the zeta at this point? The damping ratio at this point. What is this damping ratio at this point?
It's not on imaginary axis, so it must be 1.
So what about the damping ratio at this point? This is also
This
not in
is,
on the imaginary axis. So
yes, is same. On this axis, it will be same.
no, this at this point it is called the breakaway point or the break-in point. This is the break-in point. In other case, you may find breakaway point. This is the point of critical damping where zeta equal to 1. Okay. At this point, you will have repeated poles. Okay. There are two poles. There are two closed loop poles lying at this point. Because you see this is the open loop pole. When k equal to 0, this is the open loop pole. Okay. Now, as you increase the gain k, the closed loop pole is moving along this blue line. It is coming to this point, and at this value of gain, at this value of k, both the closed loop poles are lying at this point. That is, at this value of gain, the system will be critically damped.
Okay, sir.
Did you understand why am I saying it?
Yes, sir.
How do you find what is the how do you find zeta? How do you find the damping I mean ratio from a root locus? Say I'm saying that, see, if the gain is say some k, say at this point the gain is some k equal to 10, say, okay, at this point, the point that I have marked with that block, with this box, okay, I am saying that k equal to 1. How do you find what is the zeta at this point?
Sir, I can't get it now.
Just let me see. Just a minute. So, say I want to, so I want to find zeta at this point. Okay, at this point I want to find zeta. Just say I want to find zeta at this point. Is it working? Okay, it's working. So at this point I want to find zeta. What I will do is I will draw a straight line. I will draw a straight line like this, and I will find this angle. This angle, say it is the angle theta. So cos of this theta would be the damping ratio. You know this, Navketi? Do you know
Yes, sir.
this?
Yes, sir. I just remember that graph from zeta varying from 0
Right.
to 1.
Yeah. So when you're asked to find the zeta at any point on the zeta for any value of k, what do you do that? What you need to do is for you need to find out at what point we are talking about. Say at this point the gain is say 10. So you are asked to find the zeta at this point. So what you would do is you draw a line. You will find the angle of this the angle this line is making with this real of x-axis, and then find cosine of that angle. That would be your zeta. Okay, this is how you find zeta. So you know this portion. So at this point, so if theta becomes equal to 0, what would be the zeta at this point? It would be 1, right?
Yes, sir.
So at this point it would be 1, and as you move along it becomes greater than 1. These are over damped. For these values of k, the system will be over damped. And what happens in case of over damped? You find there will be two real roots, two real closed loop poles on the, I mean two closed loop poles on the real axis. So you see, maybe for k equal to suppose 20, maybe you would be getting pole over here and another pole maybe over here. So you will be getting two real poles. Two real pole means it is a overdamped system. Anyway, so what we find is that breakaway point would lie somewhere to the left of minus 2. So you do this dkds that you have already told. You find k from the characteristic equation 1 plus gs into hs equal to 0. You find k expression for k in terms of s, and then you do dkds. If you equate that to 0, the numerator part to 0, you find that s is equal to minus 0.5857 and the other would be minus 3.4142. But again, this portion, the minus 0.5857, that will not lie in the root locus. The other point would lie on the root locus. So the breakaway point would lie at s equal to minus 3.414. So the correct answer is this. So
Okay, sir.
these are the gate questions that I have, and the questions that I asked you, well, this is what I actually asked you. I will show you the picture. You can see the screen, right?
Yes, sir.
Okay. So this is what I asked you. You see, so this is a pole, right? This is a north pole I'm talking about. Okay, this is the north pole on the, this is the, these are the stationary field which is produced in a DC machine. So this is the north pole, okay. So how the flux lines look like? there would hardly be any magnetic flux lines in this air gap, right?
Yes, sir.
Why is it so?
So because it's high reluctance.
Because the reluctance is very high.
Yes.
So most of the flux would remain in this region and it would flow through these slots, complete this path through these slots. So my question was, if I am saying that it is because of the force exerted on the conductor that the DC machine is moving, then there is a contradiction. See, there is hardly any flux lines over here. How can we say that the force that is being produced is because of the current carrying conductor in the magnetic field? Because there is hardly any flux lines, right?
Yes, sir.
Did you
So,
understand
so
what I'm
force
saying?
is so force is acting on the rotor part, that magnetic part.
What? I didn't get you.
So you asked that where will the force act, on the conductor or on the rotor? So it means it's on the rotor.
Yes, I mean, I will. Why is it on the rotor? That you have to understand. Did you? My question was this: ki, most of the magnetic flux lines are completing their path through these slots. They are not in this air gap. There is hardly any flux lines you will find in this air gap. Okay, so this notion that the force is being the force that is being generated, the torque that is being produced in the DC machine is because of F equal to I into L into B sine theta. That is to some extent true, but not, that is not actually what is happening, because there are very few flux lines. If it is only because of that force, then the force produced would be, or the torque produced would be very low, and and we see that it is not that low. We are driving loads with it. So what actually happens? So you see, you see the structure in which the conductors that has been drawn doesn't is not carrying any current. This is the flux lines when when the conductors are not carrying any current at all. So you see there are no flux lines produced due to the conductors, as the conductors are not carrying any current. Okay, it is the field which is being excited, and I'm showing you the flux lines which is being produced because of the field that is excited. Okay, so the conductors are not carrying any current as of now. Now let us inject current in the conductor and see how the flux lines look like. So say the current direction is shown by dot, and if the current direction is as shown in the picture, then the flux lines produced uh, because of the current carrying conductor would be along this direction, as you can see by the dotted flux lines path that I've drawn.
Yes, sir. Thumb rule.
Yeah, right. So what would be the net flux, which is the summation of this flux and this flux? How would the
They
net?
they will be in additive, because both the lines are in same direction.
They will be additive. What
Yes,
about this?
for
What about
first.
this? What about these fringing lines? What about the fringing lines at these positions? It will not affect these lines which are perpendicular to the slots. But what about this flux lines that you can see, which is a bit bent? What would
Yes, sir.
happen to?
They will make some angle with the flux that is generated due to these flux because of coil.
So you are saying it would be bent towards the right or towards the left? How would these flux lines look like? The resultant flux lines. See, at this portion, you see the flux lines at this portion is additive. It is this flux lines produced by the field is flowing in this direction, and the flux lines produced because of the current carrying conductor is also in this direction. Okay, what about at this position? What about this slot? You see, the flux lines is along this direction, whereas the flux produced because of this current carrying conductor is in the upward direction. You see now, Kirti, what I'm
Yes, sir.
saying?
Yes, sir. Yes, I'm getting it.
So you see, it is moving towards this, right? It will get shifted, right? These flux lines will no longer be uniform. You agree with me?
Yes, sir.
So at this point in this region, the flux lines are opposing each other. The flux produced by the current carrying conductor and the flux produced because of the field winding are opposing each other. So the resultant flux, if you draw the resultant flux, it would look somewhat like this. Okay, because you see, so at this point you see this it is a tangential component along this direction, and this flux line will also have a tangential component along this direction. These two tangential components are getting added up, so it gets a bit shifted along this direction. You are getting my point, what I am trying to convey,
Yes, sir. It's very clear from the lines.
right? Okay, so now you see, now what you have read in class 12, that any ferromagnetic material will always try to align so that the reluctance of the path is minimum. So now the flux lines are bent, so it would always try to reduce this the length of these flux lines so
Yes,
that
sir. They
the
will try to be straightened.
yes, so that's why a torque will be produced in this direction. This is how actually yeah, I mean the torque is being produced in a DC machine. So this idea that the Lorentz force is the only responsible for producing torque is not very sound, because the if it was the only force, I mean it was the only force that was producing the torque, then the force would be very low, because there is hardly any flux lines in this region. However, we
Yes,
see
sir.
that the torque is quite high. So this is one thing that I wanted to convey. I wanted to discuss a few things about that PI and PID controller, which I told you the previous class about that resonant pole and all. But I didn't know that today we had class, so I missed on that part. So I have not prepared a document for that. Maybe if they ask me to take another class, I would be sharing those things with you. So the questions that were allotted to me are over. I mean, these were the questions that were allotted to me to discuss in the live session. Only a
Is
few.
this your last class, as you said earlier?
I think so. This would be my last class. Yes.
Thank you, sir.
Okay, I'm not sure though. I'm not sure what the what NPTEL people have in mind. If they ask me to take more classes, then I have to take. But officially, it was a
Yes, sir.
12.
On Tuesday, there are two classes. One of them, I don't think so. That she'll take any classes further. But one of the sir, he said he'll keep taking those classes. So,
Okay, then I have to. I mean, let me let the NPTEL people decide. I'm not sure whether they would what they have planned. Once they convey me their plan, then I will schedule accordingly. I wanted to discuss
so,
a few.
so
Yes.
will you take the further classes, or some other tutors will take on?
I do not know about other tutors, because the program is like, you are allotted some questions and you have to discuss with the people. That was the main idea behind it, to help them out how to solve it. I do not know what NPTEL people have in mind. So we actually follow what is being told to us. However, I'm a bit. I have not done exactly what was told to me, because if I had done only what was told to me, then there we would have only discussed 3 or 4 questions in a class. So
Yes, so your method was quite good compared to other.
I tried a bit. Let's see. I do not know whether I would be taking classes. I'm not sure. I mean, let them decide what plans they have. Once they disclose me the plan, or if they ask me to take classes, I will be taking it.
So, would you mind sharing your email ID?
Okay, this is my official email ID, but this is for official use. Leave it. Okay, let me just. Where is the chat box? Okay, let me just. That is my email ID. I've written on the in this this box. What is this called? This chat box. Did you get it?
So 1 minute. Yes, sir.
Okay, that is my email ID. Uh, okay, then that would be this. That would be the end. I hope. I want. Let me see if I can take another class. I will be talking about that resonant pole I discussed the previous day. Either a few controllers, PI or PID controller, if I have time. But those I do not know that whether those will be important for gate. Those are just concepts. I do not think those will be very much important for gate. But yes, we can always discuss concepts. That's not a big issue.
Okay, sir. Thank you, sir.
Okay, thank you very much. Enjoy your weekend. Bye bye.